Welcome to the first video of Unit 8 on acids and bases. In this particular video, we're going to kind of re-go over the definition of what an acid and a base are. We're going to talk a little bit about which hydrogens from an acid can be removed. We're going to talk a little bit about pH and pOH, as well as the definition and refresher of the lists for what strong acids and strong bases are. Right, so to start off with, for acids, our definition of acid that we've been using throughout the course of the year is that acids donate protons to bases. Right, proton is just the H plus ion. You'll also see it used interchangeably with hydronium or H3O plus, because as soon as the proton hits water, it will react with the water molecule to form H3O plus. Right, now, even though an acid may have multiple hydrogens in it, not every hydrogen can be lost in this way. The only hydrogens that an acid can lose are what we call acidic hydrogens. The way you can tell a hydrogen is acidic is because it's involved in a very, very polar bond, usually with oxygen or chlorine or something along those lines. Now, we have labels based on how many acidic hydrogens an acid will have. So monoprotic means one acidic hydrogen, diprotic 2, polyprotic is really anything more than one. And one of the key things about having a polyprotic acid is that when you have an acid with multiple acidic hydrogens, it's harder and harder and harder to remove successive hydrogens, right? So the first hydrogen is the strongest, then the second hydrogen is weaker, the third hydrogen, if it has one, is weaker after that. And the other thing that we should know about acids is keep in mind that pH is the negative log of the H3O plus concentration. And you can undo the negative log to find the hydronium ion concentration. Right, so we're going to keep using these equations. I would actually set these equations aside a little bit because later on we're going to go over all the rest of the different equations. So we'll add in pH, so we'll add in pOH, we'll add in what happens with water specifically, and you'll get a whole pile of equations to use, and it might be nice to have them all in the same place. Right, so this is generally what an acid is. We're working with what's called the Bronsted-Lowry definition. There are other definitions that exist, but this is the one in use in this class. Okay, so to kind of show you guys what acidic hydrogens are and kind of how they work and the difference between monoprotic and polyprotic, we have acetic acid on the left. Acetic acid is a monoprotic acid because there's only one acidic hydrogen. The only acidic hydrogen for acetic acid is this one right here, because it's in the polar bond with oxygen, right? So this hydrogen, because it's in a polar bond, electrons are drawn away from the hydrogen towards the oxygen, making the hydrogen easier to remove. And how easy it is to remove depends on its acid equilibrium constant. In this case, 1.6 times 10 to the minus 5. The other three hydrogens, so the hydrogens here off of the carbon, these aren't in a highly electronegative region. So these hydrogens aren't involved in polar bonds. That means it's not easy to take them away, so they don't get lost. These are just regular hydrogens. For a polyprotic acid like sulfuric, we have two acidic hydrogens, one here and one here. Now the thing is, for removing the first proton, these two hydrogens are identical, so it doesn't matter which one you remove first. They're both really easy to remove for the first one, because look at what they're attached to. Look at all the highly electronegative oxygens in this region right here. That makes these bonds, that makes this bond here and this bond here, both highly polar. So in fact, breaking the first bond is so easy, the reaction for that essentially goes to completion, which means that if it goes to completion, there's virtually no reactant left over. The equilibrium constant is very, very large, which is why we have that down here. After we break off this first bond, so let's say we break this bond right here, well, this bond on the right becomes slightly less polar. Right, becomes less polar because now we have this full pair of electrons here that doesn't have to worry about the hydrogen at all. So that makes this bond less polar. It makes this second hydrogen a little bit harder to remove than the first one. right? And in fact, 1.2 times 10 to the minus 2 is that equilibrium constant. The number of acidic hydrogens are based on what they're bonded to, has to be highly electronegative. Oxygen is usually a good bet. Halides are also a good bet. First electron is the easiest to remove. Every other proton gets harder after that, right? So to describe what a strong acid is, we already went over this at the beginning of the year. Strong acid, when you put it in water, completely dissociates into ions, right? So what that means is that if we have our acid, so our HA, we put it in water, it's going to completely break up. Notice how I use the yields arrow instead of the equilibrium arrow, and that will form A minus H3O plus, and that is a 100% dissociation. Right, and we also went over at the beginning of the year what the 6 strong acids were. These are our big 6: hydrochloric, hydrobromic, hydroiodic. I'll go over in a future video why HF is not actually a strong acid. Nitric acid, perchloric acid, and again, in that same future video, I'll go over why perchloric acid is strong, but chloric acid isn't. And then the first dissociation of sulfuric. Right, these will all have Ka values that are very large. And in fact, because the acid dissociates completely, we can just generalize and say that for a strong acid, the concentration of H3O plus that we would use to find our pH is just equal to the concentration of the acid, right? So if you have 0.1 molar hydrochloric acid, then the H3O plus concentration is 0.1 molar. Similarly, when we talk about bases, bases accept protons, right? So it accepts the H plus from the water, forming Hb plus and OH minus. Again, notice the reaction arrow showing it goes to completion, because this is probably going to be a strong base. Bases will generally have one of 3 different features. They can have multiple of these features, but at least one. Right? So all hydroxides are bases pretty much by definition, because notice how hydroxide right here is present in our reaction for a base with water. Anything with hydroxide will automatically form the ion when it dissociates. Ions that are negatively charged, right? So for example, CO3 2- is a negatively charged ion, because when I react it with water, what it's going to do, and this is actually a weak base, so I'm going to draw the equilibrium arrow. When this reacts with water, it's going to form HCO3- plus hydroxide. Right? So charged things can accept protons if they're negative. Molecules with center atoms that have lone pairs. This is the reason why most nitrogen-based compounds are bases. Right? Ammonia is a base because if I have ammonia, NH3, ammonia has this lone pair on the nitrogen, which can just so happen to bond with a free proton. Right? So you'll generally see bases have one of those 3 qualities. And again, just like we had for pH, for bases we have POH, which is based on the concentration of the hydroxide ion. And we can go back to the hydroxide concentration if we have pH. Another important mathematical relationship is that the total of pH and POH will add up to 14 exactly at 25 degrees Celsius. If you change the temperature, this value will change slightly. Right? Strong bases, well, if a strong acid completely dissociates in water, a strong base would do the same thing. Right? Our strong bases, at the beginning of the year, I limited you guys to just group 1 as strong bases because I didn't want to get solubility involved in the mix until we had a chance to cover it in class. Well, now we're going to expand our list of strong bases a little bit. Any group 1 and group 2 hydroxide will be a strong base. Yes, I know upper group 2 hydroxides like magnesium hydroxide and calcium hydroxide aren't extremely soluble in water the way that sodium hydroxide and potassium hydroxide are. But the portions that do dissolve will completely dissociate into ions. Right? So the parts that do dissolve will act like a strong base. So we're going to consider them a strong base. for this purpose. And just like we said for a strong acid, the concentration of H3O plus is equal to the concentration of the acid. Here, the concentration of hydroxide you can get directly from the concentration of the base. If it's a group 1 hydroxide, concentration of the base equals hydroxide. If it's a group 2 hydroxide, the concentration of the base doubled equals the concentration of hydroxide because there are 2 OH ions in it. Right, so this is our intro to acids and bases, a little bit over strong acids and strong bases. In our next video, we're going to talk about weak acids and weak bases.